Hey there, SBH4UO Section A.
Hey! I'm physicist Sarah Verdun.
And I'm mathematician Jacob Pollard.
And today we are going to be talking about magnetic forces.
Specifically, we'll be talking about the magnetic force on a current carrying wire.
Now, before we get into the complicated stuff, we're going to bring you back down to the basics of magnetic forces.
So here we have our magnet. Magnets consist of a north and a south pole. The magnetic field lines will extend from the north to the south as shown.
Now, we have three right-hand rules, which we use to determine the direction of each vector. The first one deals with the direction of current and the direction of the magnetic field, and the relationship between them. The second right-hand rule number 2, deals with the direction of a current around a solenoid, which is a tightly wound wire, and then the direction of the magnetic field around the solenoid. The third right-hand rule, and the one we are going to be talking about today, deals with the direction of a current in a wire, the direction of a magnetic field around that current, and then the force that is applied to the wire.
Specifically, right-hand rule number 3 is stated as shown. 1. The fingers of your hand will point in the direction of the magnetic field. Your thumb then points in the direction of the current, and your palm gives the direction of the magnetic force.
Now, you might be thinking, I don't understand!
And that's what we're going to be explaining to you, starting with the demonstration to show you what the heck we're talking about.
To do this, you will need some magnets, a battery, and some copper wire.
So the first step in our demonstration is to attach the base of the battery to the magnet.
Next, you want to shape the copper wire so that the wire hits the top of the battery and the base of the magnet. For our experiment, we shaped it in a heart because we love physics.
So then you will attach your wire onto the battery magnet complex.
And it will spin like so.
So now we're going to explain how the right-hand rule applies to our demonstration. First, we have our battery and our magnets. The battery has a positive and a negative end. The current then extends from the top of the battery out and around to the magnet and then up through the center of the battery from negative to positive because it is direct current. Next, we have our magnetic field lines extending from the magnet up and around, as you can see here.
Now the green circles we are drawing represent intersections between the magnetic field lines we have drawn and the current passing through the wire. These will be the points which we will use to demonstrate the right-hand rule number 3 and figure out which direction the force is applying on the wire. Now using our right-hand rule number 3, we point our fingers in the direction of the magnetic field, our thumb in the direction of the current, and as you can see my palm was facing upwards, and so the wire is experiencing a force out of the page as demonstrated by the dots and the circles. When we apply the same principle to the other side, we find that the force is going into the page, represented by the X's within the circles.
We will now show you a bird's eye view of our demonstration. So here we have our battery. The current from the battery extends outwards. These red dots represent the magnetic field that is coming out of the page. The green dots represent the intersections and the magnetic force. Using our right-hand rule, we can now see from a bird's eye view that on the left side the force extends up, and on the right side it will go down. Because the forces are acting in opposite directions, it will cause for the wire to undergo a circular motion, as you can see here.
So now that we understand the physics behind this, let's include some math by calculating the magnetic field strength.
The way we're going to do this is a series of equations that go into one long, complex equation
That we've broken down and we've shown you exactly how we got. Now the magnetic force equation is given as follows. It's the current times the length of the wire times the magnetic field strength all times sine theta. But since theta is equal to 90 degrees, sine theta is equal to 1, and we can cancel it out. Now, the current equation is given as volts over resistance. So when we sub that into our equation, we get force magnetic is equivalent to the volts times the length of the wire times the magnetic field strength all over the resistance of the wire. Now, our equation for resistance is given as follows. Resistance is equal to resistivity times the length of the wire all over the area of the base of the wire. Now, resistivity is a constant given to each material which varies, and you have to look it up. So, we plug that into our equation and you get magnetic force is equal to volts times length of the wire times the magnetic field strength over the resistivity times the length of the wire, and that is over the area of the base of the wire. Now, because there are two lengths, we can cancel them out, and we are given the new equation, which is magnetic force is equal to volts times area of the base of the wire times the magnetic field strength, all of that over the resistivity. Now, we know force is equal to the equation mass times acceleration, so we can sub that into our equation to get mass acceleration is equivalent to the area of the base times the volts times the magnetic field strength all over the resistivity of the wire. And when we arrange to isolate for B, we're given the equation mass times acceleration times resistivity over area of the base of the wire times the voltage. Because we know the equation for centripetal acceleration, which is what the wire is experiencing, is equal to 4 pi squared times the radius of the wire all over the period squared, we can sub that into our equation to get magnetic field strength is equal to the mass times 4 times pi squared times the radius of the wire times the resistivity of the material all over the period squared times the area of the base of the wire times the volts. Given that the formula for area of a circle is pi r squared and our radius is represented by r2, we will sub that into our equation and get the magnetic field strength, and get ready for this, is equal to the mass times 4 times pi squared times the radius of the magnetic motor times the resistivity of the copper wire over the period squared times pi times the radius of the copper wire squared times the voltage of the battery. And since there are two pi's, we can cancel out the squared on top and the pi on the bottom, and we're given the equation magnetic field strength is equal to mass times 4 times pi times r1 times resistivity over period squared times r2 squared times voltage.
With our long equation, we will now calculate the magnetic field strength of our demonstration. So the mass of the wire was equal to 0.0203 kilograms. The length of the wire was 0.1 meters. The radius of our contraption was 0.03 meters. The voltage is equal to 1.5 volts. This was the voltage of the battery. The rho, which we looked up, is equal to 1.7 times 10 to the negative 8. The radius of our wire was 0.00051 meters. The time that it took for it to rotate one full rotation was 0.73 seconds. Plugging this all into our long equation, we got a final answer of 0.000061649, also known as 6.2 times 10 negative 5 Tesla.
That was exhausting.
That one drains me.
Like a battery. Well, that concludes our show for today.
But it doesn't even answer. Why is there even a magnetic force around a wire with current?
Well, I guess you're just gonna have to watch
Next week on the New Year's edition.